Hey everyone, welcome to the third video from section 2.5. In this video, we're going to talk about stability of critical points and various ways to analyze autonomous equations, autonomous systems, and what their solutions look like, just based on the ODE alone, not really looking at the actual solutions. So you can do this sort of analysis without actually having to solve the equation, which can be nice depending on the situation you're dealing with. So let's go ahead and take a look and sort of see what I'm talking about in that regard. So we're going to start by looking at the thing we ended with last video, which was the sketch of this logistic growth model with a threshold. So you have the K carrying capacity, the T the threshold value that you're looking at. And now we want to talk about stability of critical points. Now I'll write this down later, but we're just going to talk about it informally now. So what do we mean by stability? By stability, we mean that if we start nearby the critical point, we should stay nearby and or get closer to the critical point over time. Instability or an unstable critical point should mean that if we start nearby, we end up running away from it. Right? If it's stable, if it attracts things to it, it's unstable if things want to run away from it. So take a look at the graph here of t versus p that we drew for the solution. Which of these critical points are stable and which are unstable? Well, if you look at that, we'll see that k, the carrying capacity, the upper one, is a stable critical point. Why? Because solutions that are below it will increase up to k, and that also solutions above k will decrease down to k. So everything nearby is funneling in towards k. That means that k is an asymptotically stable critical point. Stable means things stay put. Asymptotically stable means things converge towards k as time goes on. I'll write these words down in a second. We're just going to talk about it for now. T, on the other hand, the threshold value, that is an unstable critical point. Why? Because if things are nearby, they go further away. If you're slightly above t, you increase to be further away from t. If you're slightly below it, you will decrease more to be further down and further away from it as well. So here we have k is a asymptotically stable critical point, and t is an unstable critical point. So let me write those things down with the definitions to make things more clear, and that should help explain things a little better. So we're talking about here stability of critical points. So in this case, k is an asymptotically stable critical point, which means that solutions close to k continue to get closer to k over time. On the other hand, t is an unstable critical point, meaning that solutions near t move away from t over time. There is also the idea of a semi-stable critical point, where solutions from one side come in but the other side go away. That's in one of the problems in the back of the section, and that would be something we probably talk about tomorrow in class. So now how do you figure this out? How can you decide if something's going to be asymptotically stable or unstable from the idea? Well, you draw the phase line. So in our case before, we had this phase line, 0, t, and k, plus, minus, minus. So what does that tell us? If we're near t but not at t. If we're at t, we stay at t, and that's always the case for any critical point. But if we're nearby to t, we're going to move further away from it as time goes on, right? Because if we are less than t, we have a negative sign, so we're going to go further down. If we're bigger than t, we have a plus sign, which is going further up. So t is unstable just by looking at the phase line there. Same thing with k. If we're at k, we're constant. We don't care about that case. If we're nearby to k, we end up going back towards it. If we're below k, we have a plus sign, which means we're going to increase up to k. And if we're above it, we have a minus sign, which is going to decrease down to k. So from the phase line alone, you can determine whether or not these critical points are asymptotically stable or unstable. All right, and then the last thing I want to talk about is concavity of the solution in this case. So how do we define concavity, or how do we determine concavity? We determine that from the second derivative. So I want to look at the second derivative of p in time. Well, this is d dt of dp dt, but I know dp dt, that's just f of p. And no, this is not 0, right? We know f does not depend on t explicitly, but it does depend on implicitly through p. So by the chain rule, this is f prime of p times dp dt. So the concavity, or the second derivative, is f prime of p times f of p. So we get concave up if f prime and f have the same sign, concave down if different signs. Which means if f is positive and increasing, we're concave up. If it's positive and decreasing, we're concave down. And same thing with things being negative. So I'm going to go back up to the simple logistic equation we had before and show you why I knew what I was doing. All right, so we just look at the logistic model right here. What we'll see is if we look at f versus its derivative, we see that f is increasing up to this maximum point here, and then it drops off and is decreasing here. So here, f is both positive and increasing, so this is concave up. Here, f is positive and decreasing, so this is concave down. And here, f is negative and decreasing, so that's concave up again. Which is why I knew that at this point here, which ends up being k over 2, I have an inflection point across the middle. So if I'm above that point, I am concave down, still increasing, but concave down. If I'm below that point, I am increasing and concave up. And above here, I'm always decreasing and concave up. So from the graph of f, you can determine the concavity of your solution. Really, from f prime and f, you can determine the concavity of your solution. And from the function itself, you can determine the stability of all the critical points that are there. All right, so those are the main topics for this video. I'm now going to give you a problem to look at where you're going to analyze the critical points of a certain autonomous solution. Now, by analyze, I mean I want you to find the critical points. I want you to determine whether or not they are asymptotically stable or unstable. And those are the two main things I'm asking at this point. Where are they, and are they asymptotically stable or are they unstable? So I'm going to throw that problem up for you right now. So there's an ODE for you guys to look at. There is a cube term there, but if you think about it, you should realize the cube part doesn't actually matter. So there is a ODE for you to look at. I want you to find the critical points and analyze whether or not they are stable or unstable. Hint, you're probably going to want to draw a phase line, and then you should be pretty good for that one. All right, that was the topics for this video. Thanks for watching. And in the next one, we'll sort of deal with the comparison between getting estimates of what's going to happen just from the equation itself, or actually solving the problem. We'll see what the difference is, why one wins sometimes the other wins the other times, and sort of talk about the difference there between qualitative and quantitative analysis. Thanks a lot for watching, and I'll see you in the next one.